Hello, Bafundi. Welcome again to another episode, another lesson. Today I'll be covering a new topic altogether. So I'll be starting with our topic on momentum. So what I'll try to do is just to cover the basics of it and to do some examples together. And then what I ask you to do is that please try out some more examples for yourself. And then should there be any questions, you can always, just make a comment, or you can just ask questions. Okay, you can also get in touch with me. My email address is Mlungisi, my name, Mlungisi .m.nkosi @gmail.com. Mlungisi.m.nkosi @gmail.com. All right, enjoy the lesson. Let's begin. All right, as I said, we're starting on momentum today. So essentially, what is momentum? We don't want to waste time on the non-essentials, right? So what is momentum? Essentially, we say that momentum, we use the symbol P for momentum. We say momentum is the product of a body's mass and its velocity. Now, if you remember, from previous grades, you remember that mass, okay? In physics, we always measure that in kilograms, okay? And velocity is measured in meters per second. Now, please note I said velocity and not speed. So, in this particular case, what happens is that you are now taking the product of a scalar quantity and a vector quantity. So every time we take a scalar and a vector and we multiply them with each other, we always get a vector quantity. So what am I trying to say to you? That momentum is a vector. So what does that essentially mean? It means that we must express momentum in terms of its magnitude as well as direction. Okay? Right. Now, we say that momentum is the product of mass and velocity. All right, and as a result, that is why every time you are going to calculate momentum, you're going to actually express it in these very same units of kilograms meters per second. Okay, so that's kilograms meters per second. Right, now, very importantly, right, so what I want us to get into at the moment is just the relationship between momentum and Newton's laws. Okay. Right, now, not only can we calculate the momentum of a body, but we can also calculate a change in momentum. Now, please note this, right? So when we say a change in momentum, all right, we say it's going to be the mass, okay? Usually we deal with masses that don't change, okay? Multiplied by the change in the body's velocity. Now, very importantly, let's take a quick example of this. I've seen oftentimes there being an issue with this. Suppose I've got, let's say for argument's sake, let's say we've got a wall, all right? Someone kicks a ball and it's moving towards a wall, right? Let's say just for argument's sake, the mass of the ball is, let's say 1 kilogram. Ooh, that has to be a very heavy ball, right? The mass of the ball is 1 kg. Let's say we kick it towards the wall and it's now moving at, say for argument's sake, 8 meters per second. Okay, and then what happens is that it collides against the wall and then bounces back. All right, so in this case, let's say it now bounces back at 4 meters per second. Okay, right, if I said to you, calculate the change in momentum. I'm going to introduce another word for this just now. All right, calculate the change in momentum of the ball. All right, so you'd say to me, okay, so change in momentum, all right, is equal to mass multiplied by the change in velocity. All right, now oftentimes what our learners tend to do is that they just plug in those values. So they'll say mass, what is the change in velocity? It's final velocity minus initial velocity. Okay, right, what is our final velocity? This would be the velocity after the collision with the wall. So what would that be? 4 meters per second. What's the velocity initial? That's 8 meters per second. But whoa, we are forgetting something very important. Remember, velocity is also a vector quantity. So it means that we must express it in terms of its direction. Okay? So what we need to do is we need to choose a positive direction. So for the purpose of this question, suppose I say to you, let me choose direction to the left as my positive, so that I know in this case anything that's going to the left is positive. So what does that mean with my initial velocity? It must be positive because it's going to the left. All right, so what does that mean with my velocity, with my final velocity? It must be negative since it's going to the right. That's going to be important in answering this question. So how do I calculate the change in momentum in this case? Well, I'll say, well, my mass is 1 kilogram. We said we express mass in kilograms. What is my final velocity in this case? It's the velocity after that collision. That's going to be -4, all right? So remember, we already had this minus sign here. So minus, what is our initial velocity? That's going to be a positive 8 meters per second, all right? So in this case, what does it mean? It means that my change in momentum would actually be, that would be -4 minus 8, which gives you -12 times 1. So this is going to be -12 kilograms meters per second. Okay, now this becomes very important because then it means that I must express that change in momentum in terms of its direction as well. So therefore, it means that the momentum of this body must have changed by 12 kilograms meters per second. In which direction? Well, the negative direction. So it must be away from the wall, or you can say to the right. I hope that makes sense. Okay, right. Now, I want us to quickly introduce another term here, and that term we call impulse. Okay, right. We talk about the term impulse. Now, by definition, impulse, okay, if we talk about impulse, sorry about that, is the product of the net force, right, and the time taken over which that force acts on the body. So it's the product of force and time, okay? But if we go back to Newton's second law, what we then discover is that, well, these two put together, if you remember, what is net force? Net force is the causes an acceleration rather. So we know that this is equals to ma multiplied by the time, right? Now I don't want to bog you too much into these gory details, but what I want you to simply just acknowledge is the fact that if you think about force, it's equal to ma, right? And time is, well, time, okay? Right, look at this. I'm going to show you how this is an equivalent of the change in momentum of a body, and then relate this to Newton's second law. Now, if you think about it, this is kilograms. That's multiplied by acceleration, which is meters per second squared, okay? Multiplied by time, which is in seconds, all right? Now, in this case, what do you have? You've got two exponents. This one that have the same base. That one is +1 and that's -2. And so what are you left with? You've got kilograms meters. That -2 plus 1 gives you -1 kilograms meters per second. And so that is why then we say impulse, okay, is actually equal to force multiplied by the change in time, but that is also equal to the change in momentum, okay? Change in momentum. So they call this the impulse momentum equation, all right? And in fact, if you go back to what Newton's second law is, I'm going to show you in just a little while. So we've got a force impulse, a momentum impulse equation that says F net delta t, change in time, is equal to the change in momentum. Okay, right. If you look at Newton's original transcript, okay, what it actually states is that the net force acting on a body is equal or is directly proportional to the rate of change. Now, when you say rate of change, when you say rate, it's always division by time. It's equal to the rate of change of the momentum of a body. Okay, so in this case, we are actually applying Newton's second law once again. All right, right. Now, what I want us to do later on, we're going to have an application of this. Okay, but I'm just going to leave this here for now. As I said, I'm going to go quickly through this. Now, suppose we had a body. All right, say you've got two bodies. We've got body A and body B. Let's say two trolleys. Okay, here it is. We've got this trolley being stationary. Okay, and let's say this trolley is moving in that direction, say at whatever speed, v. Okay, and then what happens is that the two trolleys then tend to collide with each other. In a practical case, what would likely happen to trolley A? Well, after collision with B, you'd find that A has a speed that is less than V. Okay, right? And what would happen to B after collision? You'd find that it actually starts moving. So then we have what we call a law of physics that we are now applying. And that is the law of conservation of momentum. Now, please, I'm going to stay on this a little while because that is where I want the crux of our lesson actually to be. All right. So what the law of conservation, now when you use the word conserve, what does it mean? It means to keep something in the same state. Okay, so the law of conservation of momentum simply states, in an isolated system, all right, so what is an isolated system? Is where there are no external forces. All right, right. In an isolated system, the total linear momentum remains the same in magnitude and direction. Or you can simply state it this way. In an isolated system, the total linear momentum is conserved. Now, please, I want you to note and to remember this. The essence of this law is that it is applicable only in an isolated system. So what am I saying? We don't have, in an isolated system, we don't have an applied force. In an isolated system, we don't have frictional forces. So it must always be in a system where there are no external forces as such. Okay? So we say in an isolated system, the total linear momentum remains the same. So what happened? So when A collided with B, A transferred some of its momentum to trolley B. All right? Such that the momentum of the system, now please, this is where I want you to please note, we are talking about the total linear momentum of the system. What is our system in this case? It's A and B together. All right, so it means that the total momentum of A and B before collision, okay, I know sometimes they use so total momentum before the collision will now be equal to the total momentum, the sum of their momentas after collision. All right, now notice what happened afterwards. After they collided, we said B would now be moving, okay, when initially it wasn't, and then A's velocity or speed would actually be now reduced from what it was before. All right, now there are all types of different applications for this law, and by the way, that is why it's so strongly related to Newton's second law, because this is how now we come up with safety measures, particularly with cars. When you talk about things like seat belts, when you talk about things like airbags and so on, it's all in application of this rule. Now, what I want us to do, I'm going to take a question very quickly, but it's going to be a sort of self-made question, all right, wherein I want us to apply this, and I'm going to also talk about this a little bit further. Okay, right, now I'm just going to turn over the page in a few, right, so that we can continue. All right, so suppose we've got two trolleys, okay, like we did initially, trolley A and trolley B. Let's say the mass of the initial trolley is of trolley A is 10 kilograms. Okay, let's call this trolley A, and trolley B has a mass of 5 kilograms. Okay, right, so say trolley A is moving at a speed of let's just say, suppose 4 meters per second. All right, and then let's say velocity of B is 0, so meaning that B is stationary. Okay, so meaning afterwards what's going to happen? They're going to collide with each other. So what happens after they collide? Okay, so in this case, let's say after they collide, we want to find out what will be the velocity of A after they collide. Okay, assuming none of the parts of A fell off, so the mass is still the same. Okay, so B also has the same. So suppose after they collide, the speed of B, or rather B, moves at a speed of 2 meters per second in the same direction as A. All right, so what I want us to do is, first of all, I want us to calculate the speed of A, or the velocity of A after collision. And whilst I'm at it, I'm going to show you something else. They usually ask us this: is this an elastic or inelastic collision? Inelastic collision. Right, now I want us to try and answer this question together. Right, now have a look at this. I'm going to take a different color in answering. Right, so in this case, here we are. We've got trolley A, trolley B. We know this one is moving to the right. Now, please, I want you to always remember in this case, before I do anything when it comes to momentum, it is important for me to choose a positive direction first. So, for all intents and purposes, please, I'm going to choose direction to the right as positive, and I'm indicating this so that my examiner can see this, okay, so that it is clear. All right, so first of all, I want to calculate the velocity after collision. All right, now please, I want you to note we are now going to apply the principle of conservation of momentum. So what does it state? It says, well, the sum of the momentum of the momentas before collision, let's say before collision, right? Some people choose to use PI, which means momentum initial, is equal to the sum of their momentas after collision. Okay, as I said, some people prefer to use before and after. Now, what do we have? We've got momentum of A. Remember, we're taking the sum of their momentas, all right? So it means that we're going to take the momentum of body A. But what is momentum? We know it's mass multiplied by velocity, isn't it? So we're going to say the mass of A times the velocity of A plus the momentum of B. That's mass of B, velocity of B. And both of those are initial. That's before the collision. Then after they collide, that's that side now, we're going to say, well, it's going to be equal to the mass of A, velocity of A final, plus mass of B, velocity of B final. Now let's substitute. Okay, we know the mass of A, that's going to be 10 multiplied by Now please, I'm going to make this very specific. We said direction to the right is positive, so that's going to be multiplied by a positive 4, right? Plus the mass of B, that's going to be 5, times the velocity of B initial, that's going to be 0, okay? I could have just thrown a 0 there, but I want you to see it clearly. So this is going to be the mass of A, that's going to be 10, times what is the final velocity of A after collision? Sorry, that's what I'm looking for, so I'm going to leave that as a VAF, plus mass of B, that's going to be 5, multiplied by the velocity of B. It's still to the right, so we consider this to be positive 2. So all that's left for us to do now is to just take on a few mathematical gymnastics, okay? So that's going to be 10 times 4, that's positive 40, plus 0, which is equal to 10 VAF plus 5 times 2, that gives us a positive 10. So obviously now we're just simply going to take everything to the other side. So we're going to have 40 minus 10, that's going to be 30. That's equal to 10 VAF. Okay, I'm not going to waste a lot of time on the mathematics of it. Okay, so we divide both sides by 10. And what do we get for our final velocity in this case? This is going to be, sorry, I actually divided by 30 here instead of dividing by 10. Remember, what you do on the right, you do on the left. All right, so in this case, 30 divided by 10, that would give us 3 meters per second. And by the way, it is important to note that that answer is positive. What does that actually mean to us? It means that the velocity of A after collision is going to be 3 meters per second. And in which direction is that going to be? That's going to be in our original direction, which is to the right. Very important for us to note. Okay, right, I'm going to move over to the other side so that you can, I'm going to answer the second question now, right? Very important for us to state both magnitude as well as direction. Okay, right, now please, I want you to note that A was moving at 4 meters per second, but after colliding with B, it's now moving at 3 meters per second. If you were to take the momentas before collision, okay, let's just do that quickly. 10 times 4 plus 5 times 0, that gives us 40, all right? So the sum of their momentas before collision was 40 kilogram meters per second, right? Look at this. If I take 10 multiplied by 3, that gives us 30, plus this 5 times 2, which is 10. Okay, so that's 30 plus 10, that would still give me 40. And so this rule holds true, that the momentum before collision must be equal to the momentum after collision. I hope that is very clear. Now to answer the second question, right? So they ask us, is this an elastic or inelastic collision, right? What does that mean when I say that a collision is elastic or not, or inelastic? Okay, I want you to just notice whenever two things collide, and by the way, when you use collide, it's not necessarily meaning you know, a physical crash, boom, bang between two things. All right, it could be just an event, and you'll see sometimes we take people that are falling off skateboards or whatever the case may be. Right, whenever an event occurs, all right, in this case I'm talking about two trolleys colliding. When two things collide, you are likely, like in this particular case, you are likely to hear a sound. Okay, so that means what has happened, it's the principle of energy, okay, the conservation of energy, which says energy cannot be created or destroyed, but it is transferred from one form to another. So when two things collide, you are likely to get an inelastic collision, and I'm going to show you why in a few. Because some of the energy that they carried is converted into another form of energy. In this particular case, it could be sound, okay? In other cases, it could be heat, it could be all sorts of different things, all right? So in this case, what do we mean when we say something is elastic? All right, it simply means that kinetic energy is conserved. Now, please, I want you to remember, okay? If you haven't covered the principle of energy at this stage, that's fine. But how we calculate kinetic energy, we always say it's going to be half times the mass of a body multiplied by the velocity squared, okay? Now, please, I want you to note this. An elastic collision is one whereby the kinetic energy of the system once again is conserved, meaning it is kept the same. Now note once again, it means that I will take the sum of the kinetic energy of the system, meaning kinetic energy before, the sum of the kinetic energy before collision, all right? And what I'm going to do is I'm going to compare it with the sum of their kinetic energy after collision. Sum of their kinetic energy after collision. Note this. I cannot put an equal sign because I don't know whether they are equal or not. Because at the moment I'm just still testing. Okay. So let's take kinetic energy of A. So that's, we're going to say half ma va squared plus half mb vb squared. Please don't forget that square. All right, and then once again after collision, so that's initial, that's going to be half ma va squared, that's final, plus half mb vb squared. Now we're going to compare the one before of the system before and the system afterwards. If we find that the kinetic energy before is equal to the kinetic energy after, then we can conclude that this is an elastic collision. Okay, it means there was no energy that was lost. There was no kinetic energy that was lost. The kinetic energy is conserved. It stays the same, right? So if we find that they are not equal, then obviously, then we will conclude that it's an inelastic collision. It would simply mean some of that energy was converted into other forms of energy in this particular case. All right, now let's substitute very quickly. Before collision, we know the mass is 10 times the velocity, that's 4 squared. Okay, if you want, you can put positive 4, but it really doesn't matter because you're squaring that number. Anyway, that's half times 5, 0 squared. Okay, quickly, so we are going to get 5 multiplied by 4 squared. Okay, so that's 5 times 16. 5 times 16. Okay, we're going to get 80 joules there. Okay, right, please remember this one is 0. Okay, so that's half times the mass is so A is 10. Final velocity of A, please remember we said that was 3, so I'm going to substitute that there. So that's half times the mass of B is 5, and the velocity of B after collision is 2 squared. Okay, so this is going to be half times sorry, let's just put that in the calculator. All right, so I'm going to just say 0.5 times 10 times 3 squared plus 0.5 times 5 times 2 squared. Okay, so that gives us 55 joules. Now please note, ladies and gents, you've got the kinetic energy before collision being 80 joules, and after collision we found that it is 55 joules. What can we now conclude? Okay, it means therefore the collision is inelastic. But why is that? Because EK, or the sum of EK initial, is not equal to the sum of EK final. All right, so it's an inelastic collision because kinetic energy is not conserved. I hope that makes sense. These are the kind of questions that we can sort of expect when it comes to momentum. All right, so let's just take another question. All right, you can just simply pause this if you still want to look at it a little bit more. All right, but we're going to take another question in just a few. All right. All right, I thought I should just take a typical past exam question. All right, so that you can see how we apply. And by the way, there's something that I like about this because it also has part of that application of the impulse momentum question that I asked you about, or that I spoke about earlier on. So I want us to take this question together. All right, there's a couple of things that I want us to look at here. Right, now what does the question state? It says a bullet of mass 20 grams is fired from a stationary rifle of mass 3 kgs. All right, assume that the bullet moves horizontally immediately after and then immediately after firing the rifle recoils. Now what is to recoil? You know, when a gun bangs, okay, it kind of moves backwards, okay, so that's called recoiling, and they explain it there. It moves back with a velocity of 1.4 meters per second. Now they say to us, okay, calculate the speed at which the bullet leaves the rifle. Now please, I want us to look at this together. I'm not very good at drawing, okay, so here's our rifle. So initially the bullet was locked on the inside, isn't it? Okay, so so we have a bullet inside a rifle, and they had told us that it was stationary before, isn't it? And then what happens afterwards? So now then we have the rifle kind of recoiling backwards at I think they said 1.4 meters per second. Very important for you to actually draw this, or you know, to kind of interpret what they are saying to you. Okay, right, and then we've got the bullet now moving. Okay, that's our first bullet there. Obviously it would be moving in the opposite direction. Okay, right, now what we wanted to find out is at what speed the bullet leaves the barrel. So we want to know what is that speed there. Right, so what are we going to apply? We are going to apply our conservation of momentum equation. Okay, so now we're going to say, all right, so the sum of the momentas before collision, okay, is equal to the sum of their momentas after collision. Now please, I want you to keep this in mind. We said the very first thing you must always keep in mind is to choose a positive direction. Okay, I am going to assume that direction towards the right is positive. Okay, you can choose left as positive, it doesn't really matter. For as long as the examiner hasn't stipulated it for you, you've got the latitude to actually choose any direction for yourself. Okay, so right, I'm just going to call this, we said this is the rifle, so we'll call it R, and the bullet, we'll just use the symbol B for it. Okay, so I'm going to say, well, the momentum of the bullet, velocity of the bullet before collision. Now please, I want you to note something very important here. Before collision, what happened? They were actually locked together. They were actually one system together. So what I'm actually going to do instead is that I'm going to now combine the mass of the rifle. Okay, we said we'll call it R. Looks like Mr. now. Momentum of the bullet, okay, multiplied by their initial velocity. Does that make sense? Okay, even if you look at it mathematically, all right, so if their velocity was the same, okay, in a sense, because they were actually one thing. Okay, it's only afterwards that we can then separate them and say, okay, so momentum of the rifle, velocity of the rifle, final, plus, now they're separated, okay, plus the momentum of the bullet, velocity of the bullet final. Okay, so remember, together they were one system. Okay, so that's why I added their masses. They had a common velocity, right? So in this case, we know that their initial velocity was 0. Why? Because they told us it is stationary. So even if you put that whole mass and velocity there, it's still going to give you a 0. Okay, so we get a 0 for our answer there. So what is the mass of our rifle? Okay, now sorry, the mass of our rifle is rather 3 kilograms multiplied by the velocity of the rifle after collision. Remember now, it has to be minus 1,4. Okay, it's in the opposite direction. The mass of the bullet, now please, I want you to note this. The mass of the bullet in this case was 20 grams. Remember that mass has to be in kilograms. So now we need to convert those grams into kilograms. So what do? We divide by 1,000. Okay, so from grams to kilograms, you just simply divide by 1,000. So 20 divided by 1,000, that will give you 0,02. Okay, so that's 0,02 multiplied by the velocity of the bullet. That is what we want to find out. Okay, after collision. Okay, right, so please remember that becomes 0 by virtue of the fact that the initial velocity is 0. Okay, right, so let's take that to the other side. So what do we have? 0,02. Okay, minus, okay, becomes minus 0,02 VBF is equal to, if I take that 3 multiplied by 1,4, 3 times 1.4, okay, that becomes 4,2. So that's minus 4,2. So all we need to do now is divide both sides. Minus 0,02 minus 0,02. Okay, so it means that the velocity of the bullet after collision divided by 0,02. Okay, that gives us 210. Oh, that is pretty fast. So that's 210 meters per second. Okay, right, note once again our answer is positive. What does that tell us? It means that it's going in that direction. We did say direction to the right is positive, so it means that the velocity of your bullet. Okay, now in this particular question they said to you actually calculate the speed. Okay, so it's not really necessary for us to tell them the direction, because remember, speed is a scalar quantity. All they wanted to do is they wanted to find out what is the speed of the bullet. So we don't need to state direction in this case. Okay, right, let's go to the next question quickly. Right, now they say the bullet strikes a stationary 5 kilogram wooden block fixed to a flat horizontal table. The bullet is brought to rest. Okay, this is very important. So the bullet is brought to rest after traveling a distance of 0.4 meters into the block. Okay, so they tell us that so the distance between this and that has to be 0.4. Okay, that's 0.4 meters. So the distance between there and there, that's 0.4 meters. Okay, into the block, refer to the diagram. So there we are. There was our bullet. We know it was moving at 210 kilograms, 210 meters per second, right? And then it goes into a wooden block. Usually they use the word embedded, so it means that it lodges itself inside that block there. Now they say to us, calculate the magnitude of the average force exerted by the block on the bullet. Okay, exerted by the block on the bullet. Okay, right, now very important question this. So now what's supposed to happen is we seem to be sort of in the mix between talking about forces, and yet we are in the middle of momentum. Okay, so what exactly do we need to apply there? This is what now where we apply our impulse momentum equation. Okay, I know there's something that I need to do first, but please just stay with me just a little bit. Okay, So in this particular case, they want us to calculate the magnitude of the average force, okay, exerted by the block on the bullet. All right. Now they gave us a distance there, okay. They said it actually stays for 0.4 meters into the block, all right, and the bullet is brought to rest, okay. Now, something very important that we need to note here. We seem to be given something about the bullet before and the bullet afterwards, okay. Now note what I'm going to do very quickly. So in order for us to apply the impulse momentum equation, okay, I want you to note where my challenge is, why I'm going to do what I'm going to do. Right, so we're pretty sure this is what they want us to calculate, okay? The average force, we're going to find out what the net force is, all right? Now, the question is, do we know the change in momentum that the bullet undergoes? Yeah, sure. We do know the change in momentum there, all right? And what is that change in momentum, okay? It's going to be, please note, I want you to note that, it's going to be, in this case, we know that the final velocity is 0. They said it is brought to rest. We know that the initial velocity with which the bullet entered there was 210, okay? Now, we can find this, okay? The problem is we don't seem to have the change in time there, okay? So what do we do? Actually, there are several different approaches. I'm going to take you through one of them. I don't know if you can take another if you want to, but I'm not too sure if it would really be necessary for me to cover it during this lesson. Okay, right. Now what I'm going to do is, in order for me to get that time, okay, now what do I know? All right, I know that they said to me it's brought to rest. I know the distance of it, okay. I know the distance with which that the bullet traveled there. If you want to remember just in a bit, okay, I've got the initial velocity of the bullet. I've got the final velocity of the bullet, okay, and I've got the displacement that it actually traveled, okay. Right, so if you kind of remember your equations of motion, okay, right, there's one of those equations, all right, we'll come back to this, all right. So there's one of those equations that simply says Vf squared is equals to Vi squared plus 2 times A delta x, okay. Right, another equation says Vf is equals to Vi plus A multiplied by the change in time. I want you to please remember we are looking for time in this particular case. Né? Right, so another one is delta x. Let me use delta x in this case, is Vi change in time plus 1 over 2 A delta t squared, and another one simply says delta x is equals to Vf plus Vi over 2, okay, times the change in time. Right, now we've got these 4 equations. Of course, I'm just trying to help you to remember what we do there in order to find the time. Now, if you think about it, we're given delta x in this case, okay. We want the change in time. We've got final velocity, we've got initial velocity. So for me, this looks like a more appropriate equation to use. In the others, they seem to have acceleration, which is not what we're interested in, okay. Right, so now what I'm going to do, I'm going to take that equation, I'm going to say, okay, delta x, let's now substitute. What is our final velocity? That's 0. What is our initial velocity of the bullet? That's 210 divided by 2 multiplied by the change in time. Sorry, I just made an error there. So delta x, that is the displacement. So remember that our displacement in this particular case, that was 0.4. It was displaced 0.4 meters. So that's going to be 0.4, which is equals to. There's a bit of an issue with this question, but nonetheless, I'm just going to pretend like I don't see it. Right? So that's 210 divided by 2. That gives us 105 delta t. Okay, so that gives us delta t would be 0.4. 0.4 divided by 105. Okay, right. That gives us a very small time there. 3,8. I'm just going to say 3,81 times 10 minus 3 seconds. All right. You can imagine the bullet was really, really fast. For it to go in there, it's a matter of sub-seconds. Okay. Right. Now, the question is, can I now calculate my net force? Absolutely. So now I'm going to say F net multiplied by the change in time is equal to the change in momentum. Okay. Right. So we're looking for net force. Okay, now we know the time is 3,81 times 10 minus 3, okay, is equal to the change in momentum, right? Now, in this case, they said to you calculate the average force exerted by the block on the bullet. Now, if you remember Newton's third law, it says if body A exerts a force on body B, then body B exerts an equal but opposite force on A. So whether you focused on the block or whether you focused on the bullet is really going to be immaterial, because the same force is applied on each of them. All right. So now, how do we then tackle that question there? We're simply going to say, okay, so what is the mass of my bullet? The mass of my bullet, remember that was 0,02. Okay, now change in momentum, please remember that's mass final velocity minus initial velocity. My final velocity of the bullet was 0, and my initial velocity of the bullet was 210. Okay, and then what I can simply do there quickly is to, okay, all right, so let's say 0,2 times 210, okay, divide by 3,81, exponent minus 3. Okay, right, so the amount of force that's exerted by the bullet on the block, and equally so the block on the bullet, is 1102,36 newtons. Okay, right, and please remember, why am I not concerning myself with the sign there? They said to me, calculate the magnitude of the average force. So if you wanted to, you could have actually calculated it in another way. If you wanted to, what you could have done is to calculate the acceleration, and you remember F net is equals to ma, right? You've got the final velocity, initial velocity, you've got the displacement. So what you could have found was the acceleration there, and then actually use that to use Newton's second law to find that that force there. All right, hence I said to you, I'm not going to really entertain it much. Right, now, how does the magnitude of the force calculated in question 4.2? So we're taking that last question there. How does the magnitude of the force calculated in question 4.2, okay, compare to the magnitude of the force exerted by the bullet on the block? Okay, write down only larger than, smaller than, or the same. I had kind of alluded to this question. Please note there that it would be the same. And what do we use to apply that? We use Newton's third law. Okay, right? And what does Newton's third law say? Okay, it says if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. So it means whatever force that the bullet exerted on the block exerted exactly the same force in the opposite direction. Okay, right, and I hope that kind of gave you a sense of how we apply that impulse momentum equation. Right, so what I want to do is just do one last question based on momentum, and I think I'm going to be bringing this lesson to a close. I think you get the gist of it. Okay, so we'll take just one last question, and then that will be it for our lesson. Okay, right, now. All right, so we are kind of taking our last question before I just make closing comments. All right, so they gave us a question here. Okay, the diagram below shows two trolleys, P and Q, held together by means of a compressed spring on a flat, frictionless, so that's very important, okay, horizontal track. Right, the masses P and Q are 400 grams and 600 grams respectively. When the two trolleys are released, okay, please note, so what does this suggest? It means they were stationary. It takes 0.3 seconds for the spring to unwind to its natural length. Trolley Q then moves to the right at 4 meters per second. Okay, so all right, my drawing is kind of going to be terrible compared to the one that they have there. So here's our spring. We've got the two trolleys together. Both of them are stationary. Okay, so we know that they were stationary before. Okay, right, and then what happens after? Okay, collision. Remember I said to you a collision is just an event that happens, né? Right, so in this case we know that after they were released, so here they are being released. Okay, they tell us that, okay, so that's P and Q. They tell us, that's P and Q, that trolley Q moves to the right at 4 meters per second. It makes sense. So trolley Q moves to the right at 4 meters per second. So it's in that direction. Okay. So now we want to find out what is it that they want us to actually find out regarding this question. Okay. So first of all, they say state the principle of conservation of linear momentum in words. Now, all the time, ladies and gents, I want you to note, whenever they ask you to state a law, high chances are that in the next question, you're going to be required to actually use that law, okay? Right, now they say to us, okay, so they say state the principle of conservation of linear momentum. We said in an isolated system, right, the total linear momentum is conserved in magnitude and direction, or you can just simply say the total linear momentum remains the same or is conserved. Okay, right, so let's go to question 5.2 and let's see how to answer that quickly. They say calculate the velocity of trolley P. So what we want to find out is the velocity of P after collision. Okay, so what do we know? We know that the sum of the momentum before collision, or you can say initial, is equal to the sum of the momentas after collision. Okay, right, so we know the mass of P, velocity of P initial, plus mass of Q, velocity of Q initial. Now please, once again, I want you to note, before collision, P and Q were actually one thing. They were actually put together as one system. So what we could have done here instead of that is just simply to say mass of P plus mass of Q and their initial velocity there. Okay, they had a common velocity. They're moving together. All right. In some systems, you may find that in some instances, you may find actually the opposite being true. Two trolleys moving independently, right? And then afterwards, you find that they now collide and are now one system. So what you do is that now when they become one, okay, only then do you take them as, you know, just like what you did here, okay? Right, so in this case, what do we have? Right, after collision, now we separate P and Q. P final plus MQ VQ final, okay? Right, so in this case, their masses, by the way, please note they were in grams. So we need to convert that to kilograms. We divide by 1,000. Okay, so in this case, that's going to be 0.4 for P, 0.6 for Q. That's divided by 1,000. That gives us 0.4 and 0.6 respectively, multiplied by 0. Remember, they were stationary before. Okay, that's why they suggested to us that they were held together. Okay, right. In this case, so after collision, what happens? We know the mass stays the same. So that's 0.4. The velocity of P is what we're looking for. All right. Oh, by the way, I should have stated direction. Once again, I'm going to take direction to the right as positive. Okay. And the velocity of Q, that's 0.6 multiplied by 0.6 multiplied by positive 4, because that's going to the right there. Okay, so remember we've got 0 here. Okay, so 0.4 VF, sorry for dragging that out there, 0.6 times 4. Okay, that's going to be 6 times 4 is 24, so that's going to be 2,4, positive 2,4. So sorry, that's plus 2,4. Right, if we take that to the other side, it becomes negative. So that's minus 0.4 VF is equals to 2.4. So we divide by minus 0.4. Okay, and that gives us VF. Okay, take a calculator again. Actually, I should have left it open. So that's 2.4 divided by 0.4. And that gives us 6. Okay, so look at that. So we get a negative 6 meters per second. Okay, so what does that tell us? It tells us that the velocity of P, right, is in the opposite direction from our chosen direction. So the velocity is 6 meters per second in this direction, in this case rather to the left. Okay, right. I'm stating direction because they had said calculate the velocity. Now they say to you calculate the average force exerted by the spring on trolley Q. So the average force exerted by the spring on trolley Q. So once again, we're going to have that F net delta T is equal to the change in momentum. Okay, right. I'm just going to continue with this question on the other side here so that I have sufficient space. So it's F net delta T is equals to change in momentum. So it seems every time that they want to talk about force, I'll always resort back to this impulse momentum equation. Okay, right. So what is my net force in this particular case, right? Now, if you remember what they said to you earlier on, they said it takes 0.3 seconds for the spring to unwind. So it means the time that it takes there, that's 0.3, we were given that. Okay, and then what is the change of the momentum? Okay, right, I'm going to focus on Q, right? The change in the momentum of Q, the mass of Q is 0.6, right? What is the velocity of Q final? Please note it's VF minus VI, right? What's the velocity of Q final? All right, so after collision, Q was moving at 4 meters per second in the positive direction, minus, remember, this is MVF minus VI, okay? Sorry for the clumsiness there. Right, so in this case, I'm just going to put this like that there. So that's 4. That's what's the initial velocity? We know initially it was stationary. So that's going to be 0. So all that we need to do there, okay? So we're going to say 0.6 times 4, okay? And then we're going to divide that by 0.3. That should give us 8. So it means that the net force, and by the way, okay, F net is equals to 8 newtons. Okay, the average force exerted by the spring on trolley Q, So think about it. Trolley Q, the spring must have exerted a force to the right. So in this case, it was to the right hand side. Okay, right. And lastly, is this an elastic? Okay, is this an elastic collision? Only answer yes or no. Well, it's easy to answer that one. In actual fact, it's very difficult in physics to find an elastic collision. Why? Because whenever there's an event, whenever there is a collision, so to speak, between two things, there's always a energy that is lost. So I can tell you this 99.999%, unless you've got really, really special conditions, you're always going to find that the collision is inelastic. So we can answer this with a clear yes or no. So they said to you, is this collision, is this an elastic or elastic collision? Is this an elastic collision? Our answer is an emphatic no. Well, you don't need to write that exclamation mark there. All right, I hope this was somewhat helpful in terms of Newton's laws. Of course, as I said to you, you can always let me know wherever you've got challenges. I'm just going to move that paper so that those who want to see the question, right, can attempt it again for themselves. All right, I'm going to put that question just next to it there. All right. It's always important to kind of do as many questions as you possibly can. Please always remember the choice of direction is very important when it comes to momentum. Okay, and please remember that momentum is a vector. All right, now this is where I'd love to end my lesson. So I ask you, please, at the end of the lesson, please just kind of hit that like button there, and then also just remember to also subscribe to the channel, and please tell as many people as you can about it, because this is a means of us trying to help as many people as we can. Thank you, ladies and gents. Please have a good day.